Good morning. We will begin lecture 15. We will review quickly the key results from lecture 14 and build on the topic. As I mentioned, one of the key applications of multi-rate signal processing is in the form of filter banks, and filter banks come in several applications, and today we will look at one of them, which is filter banks used in spectral analysis. So before that, a quick summary. I would say that the key results from yesterday's lecture, one was a repeat of the noble identities, which said that if we had a situation where we had filtering followed by the downsampling, and the filtering was of the form h of z power m, downsampling by a factor of m, they could be interchanged. Likewise, if there was an upsampling followed by filtering, where the filtering was h of z power l, then we could interchange. And in both cases, the figures on the right turn out to be the preferred mode of implementation, because they are the ones that do the minimum amount of wasteful computations. Now, a second result, which is more for our familiarity and insight, we said that we could write down the time domain description, of multi-rate filters when we did a downsampling, in which case it looked like a convolution, except that the filter was not h of n, the filtering term was not h of n minus k, but mn minus k, where m is the downsampling factor. Likewise, upsampling can also be written in terms of the convolution type expression, where the h is n minus, it is not h of n minus m, it is h of n minus ml, well l is the upsampling factor. And of course, you can put both of them together. You look at how the input is manipulated through the coefficients of the filters, and then it gives us an expression. This helps you probably visualize what is happening in the frequency domain. So this is by way of the quick review. We also mentioned that polyphase decomposition, any filter, any signal can also be split up into polyphase components. So basically, anything that has got a Z transform, you can rewrite it in the form where you have m subpolynomials. So it could be the impulse response, it could be the signal itself. Polyphase decomposition is possible in any of those environments. So type 1 polyphase decomposition, which is the most common and widely used, and then we also have a type 2, which is helpful for us in some scenarios. Okay, so now let me quickly start with today's material and build on that. Let me ask you to think about one particular example. So here is a scenario where I have a delay followed by downsampling followed by upsampling. Okay. Before I even begin this example, I just want to reinforce that one of the key takeaways from this course should be that you have developed a lot of insight. So looking at a structure, immediately the intuition, the mathematical forms, the frequency domain representation, all of those sort of come together. So here is one such. Hopefully by the end of the discussion of this example, we can make some statements. So if I have x of n and I am looking at y of n, have a student who said that this is an ideal candidate for applying the noble identity. Right, I have filtering followed by downsampling. So the statement was that okay, from here I will go on to doing the downsampling first, downsampling by a factor of 2, and that means the expression, if you look at the polyphase decomposition, h of z power m downsampled by 1 m, this becomes h of z. So which means whatever was the argument raised to the power of 1 over m. So okay, so the argument was z power minus 1, I downsampled by half. So this becomes by argument z power minus half followed by upsampling. Upsampling by a factor of 2 preceded by pre-filtering. You can shift the delays even further, which then says you must take the polynomial and raise it to the power L. Okay, so come up with downsample by a factor of 2, upsample by a factor of 2 and Z inverse. Okay, so and the argument is applied the noble identities, and I have obtained an equal expression. Whether it is simpler or better does not matter. Is this correct? Applying the noble identities looks like it's okay. What he has done is okay. One of the rules in applying the noble identities is that you cannot get an undefined block. So basically this is an undefined block. Z power minus half is not defined, right? You cannot. So this is an undefined block. So in the process of applying the noble identity, so this is not permitted. And actually, if you do violate this rule, obviously you get this expression. Now here is where I want you to apply. If I downsample by a factor of 2, upsample by a factor of 2, what is it? Comb function. It will drop every odd sample. If I delay the input signal by 1 unit of time and then apply the comb function, what are the non-zero samples? The non-zero samples at this point, non-zero samples are the odd samples of x of n. Am I correct? Non-zero samples are the odd samples of x of n. Okay. Now, even without looking at the undefined block and saying that this is a violation, you could argue that these two are not equal, because now you take x of n, downsample and upsample by a factor of 2, that means a comb function. What is retained? Even samples. You delay it by 1 unit of time, what will still be retained? Even samples. So the non-zero samples at this point, non-zero samples are the even samples of x of n. So clearly these two are not the same. Obviously there must be some thing that you violated in going from here to here, and the violation was the intermediate step where there was an undefined block in the process of using the noble identity, even samples of x of n. So again, intuition, understanding the mathematics, and being able to apply that, all of these come into play, and it is very helpful if you are able to do all of those things. Okay, another interesting example for you to think about, and again tell me what is going on. Okay, so I have a structure that by now we are starting to get more familiar with and comfortable with. Downsample by a factor of m, advance operator, downsample by a factor of m, another advance operator, downsample by a factor of m, and m such branches, downsample by a factor of m. Okay. So this is the blocking operation. So if I fed into this structure not some input signal, but my impulse response h of n, I have a filter whose impulse response is h of n. So h of z, let me assume it is a causal filter, n equal to 0 to infinity, h of n z power minus n. So this is a causal filter, and now I want you to tell me what comes out at this point. This will be h of 0, h of m dot dot dot, those are the first branch. Second branch is h1, h m plus 1 dot dot dot. The last one is h of m plus 1, h of 2 m plus 1 dot dot dot. Okay. Now, did I make m? So this is number 1, number 2, and the last one was m minus 1. Okay, this is number m minus 1. Okay. So, h of n plus 1, h of n plus 2, h of n plus m, h of not m plus 1, it is m minus 1. Thank you, that was why probably the confusion was okay. H of m minus 1, h of 2 m minus 1. Okay. Now, what these actually represent are the polyphase coefficients of the polyphase component. So, if I were to split this into type 1 polyphase component, this would be E naught of z power m plus z inverse E1 of z power m dot dot dot, where E naught of z is summation n equal to 0 to some upper, I will just write it as summation over n, h of n, h of m n, h of m n z power minus n. Okay. So, actually what and we said that this polynomial, this sequence, this can be written as summation n E naught of n z power minus n. If you wrote that as the notation, these are the coefficients of E naught of n. These are the coefficients of E1 of n, those are the coefficients. This is the coefficients of E m minus 1 of n. Okay. So, actually what we would be doing was to actually split the filter into polyphase components and then apply them in the branches. But actually the structure itself has got so much of symmetry in it that actually if you feed the impulse response, the structure itself gives you the polyphase components. Again, it is just an observation that the structure actually, what is the underlying operation of the structure, and it is helpful for us to think of what exactly is happening when you have either a chain of delays or a chain of advanced operators followed by downsampling or upsampling. The multiplexing operation, demultiplexing operation, just a way of reinforcing what we have been discussing. Okay. So, now there is another interesting example which also brings in a lot of insight, and again I want you to sort of see how to draw the maximum understanding and insights from this particular example. See, it may seem like a simple example, but it is one of those where once you look at it closely, you see that there is a rich set of observations that can be taken away. Another example, I have the following sequence of operations: upsample by a factor of m, filter by h of z, downsample by a factor of m. So, straight away observation would be this is a structure for sampling rate conversion, fractional sampling rate conversion. But if input and output blocks are upsampling and downsampling are by m, you are not changing the sampling rate. So, really is this a meaningful or a useful operation? It turns out that when you start looking at filter banks and number of structures that we are going to be studying, the primary motive is not sampling rate change, but processing. And when you do processing, then input and output invariably will be at the same sampling rate, but some processing would have happened inside of the multirate structure. So, this is actually a very useful structure, something that we will encounter quite a bit. So, here is the labeling of the variables x of n, y of n, helpful to label a couple of intermediate variables x1 of n, x2 of n. Now, want you to just help me analyze this, but again the important insights will come as we progress. So, y of z, downsampling, so it will be 1 over m summation k equal to 0 to m minus 1, x2 of z power 1 over m WMK, that is the downsampling operation. Let me call that as equation 1. And x2 of z x2 of z. There is first the upsampling. So, that becomes x of z raised to the power m multiplied by the filtering operation h of z. Call this as equation number 2. Combining equation 1 and 2, combine equation 1 and 2, we get y of z is equal to 1 over m summation k equal to 0 to m minus 1, x of whatever is the argument of x2 of z, you must raise it to the power m. So, you find that this will become just x of z for all the substitutions, and the second term will be h of z power 1 over m w m k. So, since x of z is common, does not depend on k, I am pulling it outside the block. X of z 1 over m summation k equal to 0 to m minus 1, h of z power 1 over m w m k. Okay, so this is y of z. And of course, since you have y of z expressed in terms of x of z, we can treat this as a LTI system and write a transfer function y of z over x of z. That is your transfer function. This comes out to be 1 over m summation k equal to 0 to m minus 1 h of z power 1 over m w m k. Okay, all of this is routine, nothing new or very different. Okay, here is some additional information. Maybe this is where we start using introducing some new terminology. So, if we can get y of n equal to, if we can show that y of n, if through some processing you can show that y of n is of the form c times x of n minus n naught. Okay, that there are class of multirate systems where you will try to relate the input and output, and if this is the relationship, then if you look at the structure, c is a constant, n naught is a constant in integer. So, it says that the output is a scaled delayed version of the input, and such class of systems where the input and output are related in this fashion are referred to as perfect reconstruction systems. That means, whatever you did inside, you managed to recover or reconstruct the original signal, perfect reconstruction systems. Okay, so, that is one of the requirements of perfect reconstruction systems, is the reconstructed signal or the output signal must be within a scale factor a delayed version of that. Okay, and special cases of this, special case is when you say c has to be equal to 1 and n naught equal to 0, then what you get is y of n equal to x of n. You may or may not get it with a causal system, but this is a special case. So, now if I apply this condition to this system and say that I want the special case of perfect reconstruction. Special case of perfect reconstruction, always shortened with PR as the notation. That basically says that this must be equal to 1. The transfer function must be equal to 1, that is when you will get input output to be the same. Okay. Now, if you go back and look at the example that we looked at earlier, can you tell me what this block is actually doing? This block is 1 over m summation k equal to 0 to m minus 1 h of z power 1 over m w m k. Now, this is downsampling of h of n. Okay. So, if you downsample h of n, which polyphase component have you picked up in this case? So, if you sent in h of n and you downsampled by a factor of m, what you would get here is h of mn. This is the 0th polyphase component. So, what it's saying is, this is true if the 0th polyphase component of your filter is a constant. You got it? several things are getting linked together. Okay. So, basically this expression says that the 0th polyphase component is a constant. Now, but this structure we have encountered previously. Where did we encounter previously? Sampling rate change. Now, go back and let's reaffirm that whatever observation we have made is actually correct. Okay. Now, if I upsample by a factor of m and I want to do interpolation, perfect interpolation, what would this filter be? Low pass filter, cutoff pi over m. Okay. If I have done that, then what would have happened? I would have restricted my signal to minus pi over m to pi over m, correct? That operation would have taken place correctly. This is in the context of interpolation. So, then I downsample by a factor of m, I will get back the original signal, because if the original, whatever was the original signal, from minus pi to pi. Okay. So, basically this is a structure that we are familiar with, because when I know that when I do perfect upsampling or interpolation followed by downsampling, I will get back the original signal without loss of. What was this filter? Ideal low pass filter with cutoff minus pi over m to pi over m. Okay. That was the ideal low pass filter, minus pi over m to pi over m. What was the time domain response of this? Was a sinc function, sine pi over m times n divided by pi over m times n. This is assuming you had a scale factor of m, then you get this response. And if you remember, we actually sketched this. This is a sinc function. So, you will basically look at all of these, and the sample number m actually goes to 0. You can substitute m and then you will see that it goes to 0, and 2m goes to 0. Similarly, on the other side, it is a non-causal system, m minus m goes to 0. That is where you have the 0 crossing. Now, think of this as some impulse response h of n, and you pass it through a downsampling by a factor of m. What will you get? The 0th polyphase component, which will be, this sample will be non-zero, all of the multiples of m will be 0. Okay. So, it is perfectly consistent with that. Okay. Now, a little bit beyond, extending beyond to thinking ahead, does it have to be a sinc function? No. Anything which has a polyphase component such that the 0th polyphase component actually is a constant is this type. Now, which types of transfer functions have got that constraint? It turns out that this is what we refer to as a time domain Nyquist criterion. A lot of transfer functions which we can construct can have this property, and that will be very beneficial. So, what are the takeaways from this example? Whatever we have studied so far, all of it has got a fairly tight intercoupling, and we must be able to apply frequency domain, time domain, intuition, what happens, all of that together to get a complete picture. Any questions on what we have done? Basically, we looked at a couple of examples, applied that. If anything needs a little bit of clarification, we can take a minute to discuss that. Okay, let's look at build on the foundation that we have developed and move forward. Okay, so here is a starting point for us to do a number of very interesting observations and to build on that. So, first I would like to introduce, I am not sure if you are familiar with the term filter bank. I will assume that some basic definitions will be helpful, even if you have already had opportunity to study that. So, we are going to introduce the notion of filter banks, and this is a very rich area. It is a very vast area of research in the signal processing, particularly in multirate signal processing. So, this refers to a collection of digital filters, which have either a common input with a common input or a common output. So, basically a bank of filters, common input or output. Okay, if they have the same input and output, then it will become a single filter, right? You cannot have, so basically it is a collection of filters where they are meaningfully different. So therefore, what usually, and one of the most common realizations of a filter bank is when you want to analyze signals. You want to see what is there in the low frequency components, what is there in the high frequencies from the different frequency regions of the signal. This is also popularly known as spectral analysis. What you are essentially would like to do is take your signal, pass it through a low pass filter, we will call it as H naught of Z. Output will be X naught of N, which contains the low frequency components. Then you may take the same signal, pass it through a band pass signal, band pass filter H1 of Z, giving you X1 of N. You want to see what is the signal components in the different frequency bands, and likewise then you may go all the way to a high frequency high pass filter Hm minus 1 of Z, giving you Hm minus 1 of N. So this is in multirate terminology, this is called an analysis filter bank. Analysis filter bank, where you are splitting a signal into different frequency components, and that is why it is called analysis. You are splitting it. It is, and these signals X naught, X1, these are referred to as the sub-band signals. If X of N is the full band signal 0 to 2 pi or 0 to pi with symmetry, then each of these have got portions of the spectrum. So therefore, sub parts of the frequency information. So they call it as the sub band. Okay, so this is one type, and of course a very common application of this is when you want to play back music and you want to do a equalizer or a graphic equalizer, and this is very commonly used. So basically what you would do is take the low pass signal H naught of Z, apply a gain alpha naught, a variable gain, same music signal you can pass it through mid range filters, call it alpha 1. This would go out through a small speaker called the tweeter, slightly larger speaker called the mid range, and the other way, the base usually is the one with the largest dimensions, okay, and the high frequency components going through the tweeter H2 of Z, and this is the one that carries the high frequency. So basically you would boost and this is what you would typically see coming out of your stereo speaker system, where you have the tweeter, the mid range and the woofer. Okay, and again maybe you did not think of it as a filter bank, but that is what it is. It is what gives you the ability to enjoy music with the different acoustic settings. Okay, so this is your speaker. Okay, so the analysis bank is now explained. Now let us look at the synthesis bank, the opposite of the analysis bank. Now this is a case where you would take different signals, let me call that as Y0 of N, pass it through a filter, let us call that F0 of Z, another signal Y1 of N, pass it through F1 of Z Ym minus 1 of N, Fm minus 1 of Z, and add it all together. We will follow the notation that we introduced in the last class. We will just use a dot here, dot with the proper directions. So presumably these are multiple signals which are being combined to form a single signal y of n. Now, you may ask a very valid question, why do you have to filter them? Why? I mean, in the input case, it seemed like it was obvious that there would be a need for filtering. Where this filtering would come into play is in the following scenario. If y0 of n, how you get y0 of n, let us say was y0 prime of n upsampled by a factor of m, okay, this producing y0 of n. So, which means that y0 of n actually has got multiple copies of the spectrum, and you don't want all of them, you want to have only one particular copy. So, this f naught would be a band pass filter which takes out the appropriate sample. Another scenario that we had come across, no filtering, okay, no filtering, but is there a meaningful realization where f naught, f1, fm minus 1 are required? The answer is yes. If I want to do a multiplexer, what are these? Delays, either a constant or different delays, basically the polyphase notation, the polyphase structure comes into play. So, so this is actually a quite a versatile structure. Don't think of it purely in terms of delays, in terms of filters, it could be just simple delays, in which case it's just a multiplexer structure. So, regardless, this is called a synthesis filter bank, like the previous one was called the analysis. This is called the synthesis. You are combining signals into a single signal. Synthesis filter bank. These filters, by the way, are called the synthesis filters. I did forget to mention the previous case. These would be the analysis filters. Analysis filter bank. These are the analysis filters. So, filter banks at a very basic level are either a set of filters which are used to split the signal or to combine the signal. And very often we focus a lot on the synthesis analysis filter bank, because there are applications where synthesis filters are needed, but they often come as transposers of the analysis structure. So, more of our focus and effort is spent on the analysis filter bank. So, in this context, let me introduce some more notation. Now, one of the particularly if you want to do spectral analysis, there is something called uniform spectral analysis. Uniform spectral analysis says pass your signal through filters which are uniform in bandwidth. Okay. So, basically, and tell me what you get as the output. So, you look at filters which are uniform in bandwidth and pass your signal through that and get the output. So, when you look at it in the context of a filter bank, so basically these filters are not independent, they are actually related to each other. So, that is what I want to bring in as the next concept for us. So, if my first filter was let us call that as H naught of Z, has got this particular shape, then the next filter would be a shifted version of this. So, in other words, I would want to apply the following form: H1 of Z would be H naught of Z shifted e power minus j omega naught. So, which means my second filter is going to be centered around omega naught. Okay. Now, why did I get this particular, how did I come across this? I hope is familiar to you, because if you write this as H naught, Z is e power j omega, e power minus j omega naught, this is H naught e of j omega minus omega naught is the is where the center frequency lies, and of course you can shift it anywhere you want, positive or negative frequencies. Now, again, the structure and the framework that we are talking about, our frequencies go from 0 to 2 pi. So, it includes 0 up to 2 pi. So, basically I do not put square brackets on both sides, one is a curved bracket. This is the range in which I am interested in looking at. Now, if I want to analyze it using a set of M filters, bringing spectral analysis into a more of a structured multi-rate framework, M filters, and I want them to be of uniform size, then each of the filters, this implies each of the filters must have a bandwidth 2 pi over m. Each filter must have bandwidth, I will not say equal to, basically it should cover 2 pi over m, so that you can cover the entire spectrum. It may be slightly wider. So, typically what you would find as the structure of these filter banks would be, let us say that this goes from minus pi over m to pi over m. The next filter would be centered around 2 pi over m, but since the original filter was slightly wider than pi over m, then what you find is that there is a little bit of overlap between the two adjacent channels, and this is very deliberate because these are practical filters. So, if this is H naught, this would be H1, and in this case H1 of z is equal to H naught of z e power minus j 2 pi over m. Okay. Now, this we do have a notation for this, we will call it as Wm, Wm raised to the power 1, and of course H2 will be shifted by to 2 pi 4 pi over m. So, if this is H2 of z would be H naught of z w m squared and so on, and that would give you the entire range of filters, and this is a very common structure that we would come across in filter banks. Whole spectrum 0 to 2 pi divided into m equal portions, and you define filters that will cover each of those portions. Now, this is a case where again introducing some new notation. So, if I were to look at the our description of filters and filter banks, the terminology that we would apply is take a typical low pass filter. It has got 3 zones or 3 regions. This is omega 1, this is omega 2. So, 0 to omega 1 I am drawing only in the positive frequency. So, between 0, 0 and pi. Okay. If it is a real valued filter, then this is sufficient. This would be the pass band, omega 2 to this region is the stop band, and what comes in between is the transition band. Okay. So, the filter structure that we drew in the previous case, where is the overlap happening? In the transition band. Overlap in the and invariably that is where you would expect them to overlap, and transition band in many ways is a do not care but care band. Basically you do not really worry too much about it, but you want to because in multi-rate if you are doing downsampling, then you want to be sure that this will not cause you aliasing, but it is one of those things where that is not where the signal of interest lies. So, this is typically what happens, that you have filters that will overlap in the transition band. Okay, this is the common framework. So, this is what we call as overlapping in the transition band. Now, there are 2 other, again since we are talking about terminology, let me just introduce 2 more terms. If you have filters of this type, these are called non-overlapping filter banks. That means they do not overlap at all. There is no common signal between the 2 filter banks, and of course there are yet others where there is a significant amount of overlap that is introduced. So, actually the pass bands themselves overlap. Okay, so these are overlapping in the pass band, Okay, and there are, based on your applications, you may design one of these kinds, and so notation wise, overlapping without any other specification, you assume it is in the transition band. Otherwise, you can specify it as a non-overlapping or significant overlap, which means that the pass bands themselves will be overlapping. Okay. Now, just as we did the case of ideal filters for downsampling, upsampling, interpolation and all of that, we do have a case where you look at the ideal spectral analysis scenario. So, the ideal spectral analysis scenario, let me describe that for you in the following way. The ideal spectral analysis scenario would be a filter bank which had the following structure. It had H naught of Z from minus pi over m to pi over m, and so basically it is a brick wall filter from minus pi over m to pi over m. Then H1 would be another brick wall filter going from pi over m to 3 pi over m, which means its center frequency would be 2 pi over m. And then the third filter would be centered around 4 pi over m and so on. And of course, the last of the filters when we get to 2 pi will be H naught itself. This will be back to H naught, this is 2 pi, this is 2 pi minus pi over m. Okay, this is 2 pi minus pi over m, and you can look at some other filter which has the center frequency. Basically, you have covered the whole region. All of them are brick wall filters. Okay. Now, some very interesting observations, and then how we can take it up from here. Now, if H naught, of course, as we have drawn it, is a low pass filter, it has got a symmetric magnitude response, which means that H naught of n is real, not that it is important, it is just an observation, is real. Okay. Along the same lines, what can you tell me about H1 to Hm minus 1? They are all band pass filters, impulse response complex, because they do not have a symmetric mirror image frequency response. See that it is going from 0 to 2 pi. Okay. So, it does not have, so these have asymmetric magnitude response, and that means that you have a complex impulse response. Hi of n is complex. No, I chose it that way. So, basically what I am trying to say is, even if I start with H naught symmetric, of course you can take H naught asymmetric as well. Basically what I am saying is, even if H naught is symmetric, which when you design a low pass filter, you invariably you will design using one of the known methods which would give you a real impulse response. But the minute you construct your filter bank, the rest of your filters are complex filters. That is the observation. Now, if you want to design your low pass filter also as a complex filter, no problem, it can be done. Okay, even in that case, when you shift them, the impulse responses still remain complex. The key observation is that the impulse responses become complex. So, I equal to 1 to m minus 1. So, this family of filter banks has got this property. Okay. So, that is a observation that now there is yet another important result that is very important for us, and you may or may not have encountered this in the context of the assignments. It's a problem in Oppenheim and Schaefer. So, if I have a signal whose response looks like this, okay, it is omega naught, this is omega naught plus 2 pi over m between 0 and 2 pi, 0 and 2 pi. Okay. Again, spectrum of this type given to you says it is a complex signal, it is a band pass signal which contains frequencies from omega naught to omega naught plus 2 pi over m. So, if I call this, this is x e of j omega, if this corresponds to some x of n and I downsample this signal x of n downsample by a factor of m, this is x of mn, will there be aliasing? Will there be aliasing? The easiest way to answer that question is you take x of z, produce the sequence multiplied by the comb sequence, that we call that as x1, this is the multiplied by comb sequence, multiplied by the comb sequence, that means you will get the multiple copies and the scale factor, then you get the downsample signal. Before you get to the downsample, right here itself we will get to know the answer whether there, because you are going to get shifted versions. So when you look at this, the shifts are by 2 pi over m. So which means that the first copy of this signal is going to be shifted by 2 pi over m. It will be, if this is omega naught plus pi over m as the center frequency, the center frequency for the next one is going to be omega naught plus 3 pi over m, and it will be omega naught plus 5 pi over m, and you can see that eventually it will go a full circle and come back to the last one appearing somewhere in this region. Okay, so the last copy. Okay, so they should be of equal size. Now, the observation is that when you have a signal whose band limit is 2 pi over m, regardless of where it lies in the frequency axis, you can downsample it without aliasing. So such a signal, this signal can be downsampled by a factor of m by m without aliasing, and this is a completely general result, has nothing to do with. Now where does this find its application? Go back to filter bank. If I have been able to contain my signal to a bandwidth of 2 pi over m, which is what I would like to do in the case of a spectral analysis system, after the filter bank, you remember we drew the filter bank, I can actually downsample without loss of generality, downsample by a factor of m. Okay, so I can, if I have managed to do the band limiting. So we have covered several concepts in today's class. We have introduced the notion of filter banks, analysis filter banks, synthesis filter banks. We have shown that the relationship between the filter banks is such that you want to cover the entire spectrum, and invariably it is done through shifted versions of the original spectrum. So if you want to have a set of m filters, each of them will cover 2 pi over m. You can have different categories, overlapping, non-overlapping, or significant amount of overlapping, and then we also said the ideal case would be when you had these ideal low pass filters, starting with an ideal low pass filter, and then you generate the shifted versions. And we have made the observation that such signals can be downsampled by a factor of m. So take all of this information that we have developed for filter banks and then now introduce polyphase decomposition, and you will find that there is a very rich interlinking of the concepts, which tells us, okay, this is a area where multi-rate signal processing is going to give us a lot of new insights compared to just thinking of it as a black box which gave you some outputs for the spectral analysis. So we will pick it up from here and look at what insights we can get from the point of view of the multi-rate filter banks and the concepts that we have introduced in today's class. Thank you. We will see you tomorrow.